Then we'll get on to the content of the session. So my name is Denny, like I said. I am the owner and principal consultant for Denny and Associates Consulting. I've worked on about 7 books, including both Securing SQL Server, which is my solo project, and the SQL Server MVP Deep Dives. If you haven't had a chance to pick up a copy of that, I would highly recommend doing so. 50 some odd authors working on that book, over 1,000 years of experience went into the MVP Deep Dives book. I've written a bunch of articles for various websites and magazines, including SQL Server Magazine. I am a Microsoft MVP for the SQL Server product. I'm a Microsoft Certified Master for SQL Server 2008. I'm a VMware vExpert. I'm an EMC Elect Award winner. And on top of all that, I'm also a Microsoft Certified Trainer, which means I spend way too much time standing up here and not enough time actually working for a living. So I've broken down today's session into 5 basic topics. We're going to talk about the various kinds of indexes in SQL Server. We're going to look at some of the common misconceptions about indexes in SQL Server. We're going to look at some of the downsides that come along with adding indexes to your databases. We're going to look at some of the advanced tuning techniques, and then we're going to get some time for Q&A at the end, hopefully, depending on how long this all takes. Feel free to ask questions during the middle of the session. I'm more than happy to answer them throughout and kind of steer this however the questions go. If we get away from the slide deck a little bit, so be it. I really don't care. So there are 5 basic kinds of indexes in SQL Server that we're going to be looking at over the course of the next 45 minutes. Clustered, non-clustered, full text, XML, and then the brand new column store indexes that were introduced in SQL Server 2012. There's also the semantic search model available in SQL Server 2012, of which I know absolutely nothing about, so I will not be talking about that at all. I'm sure there's somebody here at the conference that does know about it, but I am not that guy. So clustered indexes, these are your actual tables. When you've got an actual clustered index on the table, it simply replaces the entire table with the actual information that's stored within that table. When I talk to .NET developers, which I know there's not very many of here, I tell them that it's basically a full copy of the data. It's the same structure, the same object as the actual physical table. When we create a table without a clustered index, it builds it on a set of data pages within our database. When we create that clustered index on top of that table, it then reads all that data, writes it all to a new set of pages, and sorts it based on whatever our clustering key is. We can actually have up to 16 columns be part of the index key for our clustered indexes. I would certainly not recommend doing that. The reason you don't want to do that is going to waste a ton of space in your non-clustered indexes, radically hurting the performance and the storage capacity within your database. If you're going to be using XML indexes, we actually need to remove one from that list of columns that we can use, because the XML index is actually going to require a specific hidden field be added to the clustering key. By default, when we create tables in the GUI in SQL Server, or if we create a create table, set a column as the primary key, that primary key is going to take over as our clustered index. We typically want that clustered index to be some sort of ascending value, not some sort of random value like a string or a GUID or some sort of long, ugly string that's going to make a mess of our data. Whenever you create a table with a clustered index, it's always got to be on that same file group as the actual table that you're creating it on. If you create a clustered index on a different file group from the table, SQL Server will actually move the entire table to that new file group for you, which can make things very, very confusing if you don't realize it's doing this. One of my friends based out of New Jersey in the US, he actually had a client call him and ask him to take a look at their system because they had 3 file groups on their server: clustered indexes, tables, and non-clustered indexes. And they could not figure out why their tables file group was totally empty. This was a rather large company. He felt rather bad billing them 4 hours worth of time to take one look at their system and go, well, there's not going to be anything in there, and this is why. Not to say he didn't charge them for 4 hours worth of time, but he at least felt bad about it at the same time. Whenever we're building our clustered indexes, we want them as narrow as possible. This goes along to working with our non-clustered indexes, because if we make our clustering keys very, very wide, our non-clustered indexes have to maintain that data in every non-clustered index that we have, wasting a lot of space, wasting a lot of memory, slowing down the general performance of the entire system. While clustered indexes are not required, they are highly recommended for all your OLTP tables. There are lots of systems out there that do not have them and work just fine, but for the most part, they are going to be recommended. Now, when you get into data warehouses, that recommendation is going to be reversed. Most of your large fact tables are probably not going to have clustered indexes on them. And the reason for that is because clustered indexes, or rather, the reason for that is because the primary key on your fact tables is typically a very, very wide set of columns. 4, 5, 6, 7, 8 columns sometimes. So having that being your clustered key does not make a whole lot of sense in most scenarios. It's actually a lot easier and less expensive to simply use a heap, because then we simply put the row ID into all the non-clustered indexes, and our performance is typically fine because all our fact tables simply have all the new data inserted at the bottom of the table anyway. With our non-clustered indexes, we can actually have up to 999 non-clustered indexes per table in SQL Server starting in SQL Server 2008. For the older versions of SQL Server, you're actually limited to 255 non-clustered indexes per table. Now, that's not to say you should be going out and creating all these non-clustered indexes on your tables. That will actually hurt your performance quite a bit. We'll talk about that more in a little bit. The reason this number has actually been increased is actually, again, for data warehouses. A lot of data warehouse developers were having a problem with the fact that you could only have 255 non-clustered indexes per table. So they had to go to Microsoft and request that they increase this number up to 1,000. I don't know why they stopped at 999, but that's probably simply to stop people from shooting themselves in the foot and causing more performance problems than actual performance help. Like the clustered indexes, we can have 16 columns in our key for the non-clustered index. And unlike the clustered indexes, we want these key columns to be as useful as possible. So nice wide keys are perfectly acceptable. So if you need a non-clustered index that has 6, 7, 8 columns in it, that's perfectly fine. You can even go more than that, whatever makes the most sense for the query that you're writing. On top of those key columns, we also have include columns. These are our non-sorted columns. If, God help you, you're still using SQL Server 2000, these are not going to be available to you. This was introduced in SQL Server 2005. What the include columns do is they allow you to add extra columns into your non-clustered index so that while you're querying for these various columns in your query, you can return them back without having to go do key lookups down to the base table. If you ever see any sort of operation like key lookups or bookmark lookups in your execution plans, when you actually run the queries, these include columns are going to be what solve those performance problems. A lot of the times we'll see these in development and not think they're that big a deal. Then we're working on 10, 15, 20 rows. As soon as we move that into a production environment, we throw a few 100 million rows behind it, all of a sudden our performance is going to go down quite a lot, because instead of doing 5 extra logical I/O, now suddenly we're doing 5,000 or 500,000 logical I/O. And now all of a sudden we're going to have all sorts of performance problems just simply by not having these extra columns as included columns. Our non-clustered indexes are always going to contain the key columns from the clustered index when there is a clustered index on that table. Now, this clustered index columns, not necessarily visible when you look at the schema of the actual non-clustered index itself, but those columns are being stored there. That's how SQL Server is maintaining the relationship back to the actual clustered index. Now, the interesting thing is if you write a query that uses those or returns those columns, SQL Server will actually return those for you back to the screen without actually needing to go back to the base table, because it's simply got the data. It's just not showing you that information. But those columns are there and they are stored there as part of the relationship. Now, when you have a heap or a table that doesn't have a non-clustered index, it's actually going to store the row ID instead of any sort of clustering key, because there isn't a clustering key at that point. That row ID is going to be 8 bytes wide. So if you've got a table that's got a primary key wider than 8 bytes, that's when it starts to make more sense to have it as a heap over a clustered index. Non-clustered indexes, unlike clustered indexes, can be stored in any file group on the system. So this gives us a lot of flexibility as to where to put the I/O when we're creating all these non-clustered indexes. It's very common in very large systems, depending on how the storage is laid out, to sometimes have multiple file groups. Put the clustered indexes in the heaps in one file group and the non-clustered indexes in another. That gives us the ability to control where all this extra I/O is going and spread this workload out as all our checkpoints are writing all these changes to disk. It also gives us the ability to put extra spindles underneath our queries so that we've got extra I/O capabilities when running our various select statements when we actually need to go down to the disk to pull information off the disk. A really nice feature that was introduced in SQL Server 2008 that not a lot of people are using is filtered indexes. So anybody actually using filtered indexes today? A few? All right, cool. So what the filtered indexes do is they let you put a where clause on your index creation statement. This makes your index significantly shorter depending on the kind of workload that you're dealing with, the kind of data you're dealing with. So the typical scenario that I like to talk about when looking at filtered indexes is an employment table or an employee table in a human resources database. So a typical table, employee ID, first name, last name, hire date, termination date, where the termination date is going to be null if you still work for the company. Basic table makes sense. Well, when you're working with a human resources application, 99% of your queries probably, you're looking for employees that still work for the company. So there's not really much point in having all the people that don't work for you anymore listed in the index. So we can put a filter on that index where termination date is null. And that way the index only includes our currently employed people. Because frankly, the bulk of the table is going to be people that don't work there anymore, especially if you're in like a retail environment or really any company that's got some sort of entry-level position like customer service or something like that. You're going to have fairly high turnover pulling a lot of people through that system. So if we can remove all those people that don't work there anymore, any queries that we run against that non-clustered index are going to be much, much faster because there's going to be much less data being stored in it. The B tree is going to be a lot smaller, and there's just going to be a lot less rows that have to be filtered through to actually find the rows that you're looking for. I find that this is used a lot less than it potentially could be. The only catch to these is you have to know the queries that you're actually building before you can actually build these filtered indexes. Because you have to look at the actual queries that are going to be run and go, is this specific parameter always going to be set this specific way? So when you're looking at something like a termination date field or an active flag, that can make a lot of sense. So one of my clients, I implemented filtered indexes for them on their system. They've got, last time I looked at the table, it was about 1.5 billion rows in this table. And they're adding data at the rate of about 50 to 70 million rows a month. So a fairly large table. And there's an active flag on that table. Before I put the filtered indexes on there, we had probably about 12 indexes on this table that had all 1.5 billion rows. But 98% of the queries that they run against this system are looking for where the active flag is 1. So we simply created filtered indexes where the active flag was 1 and created nice small indexes that were just a couple hundred million rows. System performance shot through the roof, as did the amount of memory we had available for other objects, because now suddenly we're not storing all these extra pages in memory, and on top of that we then turned on data compression to make the indexes even smaller and even easier to deal with. Now, one thing a lot of people don't know about SQL Server or databases in general is that all non-clustered index and really all indexes in general have to be unique. We as people have duplicate data. This is kind of a given. There's lots of people with the same name. Now, SQL Server needs to know how to handle all this duplicate data. And it does this through a hidden field that's put on all your non-unique indexes. And this column is called the uniquifier column. What this column does is it's simply an integer data type that's used to track which row it's dealing with when it comes to this duplicate data. So in the example table I've got here, we've just got a mythical table that's where the only index or the only column that we're indexing is the employee ID column. And as SQL Server goes through, it finds the first 3 rows, employee 1, employee ID 1, employee ID 2, and employee ID 3. And there's no duplicate, so it doesn't need to put any sort of value in that uniquifier field. When it gets to employee ID 4, it finds the first row, it doesn't need to do anything. When it gets to the next employee ID of 4, well, now suddenly we have duplicate values. So it goes to the first row, and it puts a uniquifier value of 0 in, and then it goes to the second row that's got the number 4, and it puts a uniquifier value of 1 in. As we continue going, it gets to another set of duplicates, in this case employee ID 7, and it puts uniquifier values of 0 and then 1 in again for the employee ID of 7. This way we can create this distinct data that we need to actually maintain this index. The reason I bring this up is because this needs to be accounted for when we're building our indexes. So if we're building non-unique indexes, every one of those rows is going to be 4 bytes longer than we think it is, because we've got this unique identifier, or this uniquifier column sitting in the index. And you can see this if you run dbcc page and actually look at the properties of the, or look at the actual index page. You'll see this data sitting in there. We also need to keep this in mind if we have incredibly large tables that have lots of non-unique data, because this uniquifier column is an integer data type, and we do have to keep that in mind, that if we overflow this column, we will get an error message back saying that we've overflowed the uniquifier column. And we need to know what that column is so that we can go figure out what the problem is. In this case, the problem would be that we've got too many employee ID records of 4 or 7 in this specific table. So full text indexes, very different from our previous 2 kinds of indexes. Clustered and non-clustered indexes, those are going to be used automatically every time a query is run, however the optimizer sees fit to use them. Full text indexes, on the other hand, are not used automatically. They're created very specifically, and then they're accessed very specifically using a different syntax than the normal select statement. What we actually have to use is these predicates: contains, contains table, full text, and full text table. If you've ever written code that searches the Microsoft Search service, this is going to use a very similar syntax to what you're used to seeing with Microsoft Search. Now, a lot of people think that full text can only index plain text data, which is actually not true. It can actually index any kind of data that you throw at it that it understands how to read. So if you throw Word documents at it, it can read those. You throw Excel files at it, it can index those files. You can index PDFs, basically anything you can give it the DLLs for. The easiest way to put the DLLs onto the system so that SQL Server can process the data and read through the files is simply to install the software that comes with it. So if I need to be able to index the values inside a PDF document, simply install Adobe Acrobat on the server. Sysadmins may not like us to do that, so they may require that we actually go and register those DLLs manually on the system, which can be done. It's a royal pain. Make them do it if they want to do it that way. The nice thing about the full text index is it's a very natural language search functionality. So think of it as a Google or a Bing style search. The end user can simply type in a very basic set of words and get back information without us as developers or DBAs having to format that search into a more traditional where clause. And because it's a full text search and it's pre-processed all the data, we can actually search for values in the middle of the field without having to put wildcards on either end, which obviously don't perform very well. Some people will try to index XML documents with full text search, and that does not necessarily work very well, depending on what your requirements are. If you're looking for simply searching through the values of the XML document and returning a matching document, that will work okay, because the XML is simply going to be indexed based on the values. If, however, you need context of the XML values, full text index is not going to be the way to index these documents. The best way to index these documents at that point is actually going to be to use the XML indexing, which I'll talk about in a few more slides. Now, there's a couple of different full text indexing engines. So who's using SQL Server 2005 and below? Anybody? Few people? Okay, I'm so sorry. You might want to upgrade to a newer platform. There's a couple more that have come out since then. So in SQL Server 2005 and below, Your full text indexes are actually created and managed outside of your database engine's database files. So these are actually stored in a separate folder called ftsearch, and they're now backed up with the database. If you haven't helped you, anybody in here still using SQL 2000 and you're using full text search and you back up and restore your database, you may have seen this, the full text indexes actually do not get backed up and restored automatically. You actually have to back them up manually because they're outside of the database's control completely. In 2005, this was fixed and the full text indexes were at least backed up with the database and restored with the database. The big downside to the full text engine in SQL Server 2005 and below is the order of operation that things happen in. In 2005 and below, when you run a query joining to a full text index, the entire full text index is searched for whatever predicates that you feed it. Whatever matching rows are found is then returned to the database engine, and then SQL Server searches those specific rows looking for any other of your T-SQL predicates. So if I search a table for last name equals Cherry, and then do a join to the full text index on that table, and tell it that I want to see anything with the word Smith contained within the full text document, it's got to search the entire table for the word Smith, return any matching rows back, and then search those matching rows for the word Cherry, for the last name Cherry. Not exactly an efficient operation when you're talking about really, really large tables. Keep in mind this engine was designed for SQL Server 7 in 2000 when the largest rows or the largest tables in most systems were in the millions of rows, and that's it. So if we suddenly throw 1 billion rows at this system, it's not going to perform because it's simply not going to be able to scale to these really big numbers. That's why in SQL Server 2008, Microsoft changed the way a lot of things are happening. First thing is, all the data for the full text index is now stored inside the database. If you've upgraded a database from SQL Server 2005 to 2008 or higher, and you look at the file groups that are created, you'll notice that there's a file group with some really strange looking name that's about that long and isn't something that you chose. That would be the old full text indexes that were outside the database getting moved into the database. SQL Server simply creates an NDF file with the same name as the folder that the data was being stored in before. It then just dumps all the data into it in the new format, and you're ready to go. In 2008, we're still using the Microsoft Search service to do the work. So in 2005 and below, all the searching of data, all the indexing of data is all done by the Microsoft Search service. So we have this huge dependency on the Microsoft Search service. So if you look at the CPU load of a 2005 server running full text search, you'll see the Microsoft Search service is using a lot of CPU, potentially even more than the SQL Server. In 2008, you'll see that CPU number change rather dramatically, because the Microsoft Search service is no longer doing the actual searching of data or the indexing of data. It's simply doing some basic word breaking and passing all that information back to the SQL Server database engine, and then the database engine is doing all the actual looking up of data within the actual full text index that's stored in its database. The other thing we've changed is the order of operations that we are doing things in. With SQL Server 2005 and below, we were searching the full text index first, and then searching the table based on whatever rows came out of the full text index. Now we're doing the exact opposite situation. We search the normal table first using our normal T-SQL predicates. We take whatever rows come out of that, and then we search our full text index based on whatever rows those are. In most cases, this is a lot more efficient. There are certain cases where this is less efficient because of how the data is written to the full text index and what data you're looking for. Unfortunately, there's no way to switch from the old engine to the new engine, or rather from the new engine to the old engine. So all you're stuck with is the new way of doing things. Unfortunately, the only way to go back to the old engine would be to still be using SQL Server 2005. Microsoft does have a performance note listed up on the knowledge base. If you're using full text indexes, they highly recommend that you have an identity or some other sequential number. In 2012, you could use a sequence just as well, as the primary key for your table. The reason they want you to do this is because that's going to improve the index join capabilities between the full text index and the actual traditional non-clustered search that's available to you, because it's going to have all those columns available already. So XML indexes, fairly cool technology, allow you to index specific nodes of an XML document within the SQL Server database engine. So if you've got an XML data type column in a table, searching through that can be extremely painful for SQL Server to go through. By adding an XML index on top of that column, we can dramatically improve the performance when querying against that table. You can have up to 249 XML indexes per table. So there's a huge amount of flexibility here. Why you would need that many, I have no idea, unless you had a lot of XML data type columns in one specific table. It does require having a clustered index on the table, so there's no way of doing this with an actual heap. When you're setting up your XML columns and your XML indexes, there's two different kinds of XML indexes. We have primary XML indexes and secondary XML indexes. The primary XML index gets created first, and then secondary XML indexes get created after the fact, creating additional search capabilities. When you're creating your XML indexes, you cannot create multi-column XML indexes. So XML indexes are created on a single column and only on a single column. If you need XML indexes on 2 or 3 columns, you simply create a single primary XML index on each one, and then you create a secondary XML index on each of those primary XML indexes. In SQL Server 2008 R2 and below, having XML indexes on a table disables your ability to do online rebuilds if you're using the Enterprise Edition of SQL Server. If you need the online index rebuild functionality that you have without XML indexes, upgrade to SQL Server 2012. SQL Server 2012 does not have that problem. If you're using XML variables, these are not going to be available for your XML indexes. This is only going to work on actual tables within your database. So when you create the primary XML index, what's actually happening under the covers is SQL Server is actually creating a new table on the SQL Server database. This new table is going to contain the primary key from the base table and 12 additional columns of information. Those 12 additional columns of information are going to contain everything there is to know about the XML document that you've stored in that table. It's basically going to shred that XML document, store the entire structure and the data within that specific 12-column structure. So this primary XML index is effectively a clustered index on that specific hidden table. If you're using XML indexes, expect your storage requirements to skyrocket. It's not uncommon to see storage requirements for tables to go up anywhere between 200 and 500% when creating XML indexes on the table. That's because we are taking XML data and shredding it and storing it in uncompressed tables and then creating indexes on that table. Our secondary XML indexes, these are effectively non-clustered indexes on the hidden table. Not effectively, that's what they are. They are simply the non-clustered indexes on that table. There's 3 kinds of secondary indexes that we can create on our XML data. We can create path indexes. These path indexes are based on the node ID, which is the path, and then the value of the data within the non-clustered, or within the XML document. The value index is built on the value of the data, then the path. So it's the same columns, but reversed. The property index is based on the clustered index value, the path, and then the actual data value of the XML document. Which one of these you need is going to totally depend on how you write your XPath query that's searching the data within your XML documents. The easiest way to figure out which one of these you're going to need, create all 3 of them in your development environment, run your query, get your query working the way you want so that it's returning the data you expect, and then look at the execution plan to see which one it's actually using. Because depending on how you write that query and what order you have things in your XPath will determine which one of these indexes that you're going to use. Typically, a development environment is a much smaller subset of data, So it's fairly easy for you to create these indexes in your development environment and actually figure out which one's going to be the best option to use. So some common misconceptions about indexes. So I see this one from developers all the time. Indexes don't require maintenance. This is where consultants make the bulk of their money. Is simply running alter index rebuild or alter index reorg statements against indexes and fixing a lot of performance problems that way. Just like everything else in the IT world, indexes obviously need a little bit of tender love and care and a little bit of cleanup every once in a while to make sure that the index is properly laid out on the disk and that it's not fragmented across the entire hard drive. When you're looking at index fragmentation, there's a few different numbers that you're going to be looking at. One is going to be the percent of fragmentation. The other is going to be the number of fragments that are on the disk. And you can pull these from sys.dm_db_ physical stats, physical stats. Specifically, the one you want to look at is the number of fragments on disk and how big those fragments are. If you've got an index that's made up of 20 gigs of information and it's 2 or 3 large fragments, that's going to work okay because SQL Server is going to be able to simply scan through all the pages. They're all going to be right next to each other within the data file. I'm assuming that your data file is not fragmented across the entire hard drive physically. However, if you've got that same index and it's broken up into 70,000 fragments and it's kind of spread all over the data file, when SQL Server goes to read through that index looking for information, the head is going to be sitting there bouncing all over the place as it's trying to find all these various pages. And it's got to load them all up into memory, and then it's got to put them all together so it can go scanning through all this information. So by having it fragmented across all these various fragments, we're going to be making a mess of everything, and it's going to take a lot longer to find the information that you're looking for, especially if you have to scan through various objects looking for information. Another one I see occasionally, if I create one index for every column in the where clause, everything's going to work just fine. No, this isn't actually the case, although it may look like it when you actually start running very basic queries against the database engine in the development environment. That's because there's not very many rows there. SQL Server will almost never use multiple indexes against the same table as part of the same query. That's not to say it won't happen, but it's very, very unlikely that it will by itself. When we're building our non-clustered indexes, we need to put all the columns that we're using in our where clause, all the columns that we're using as our join predicates to do filtering, all into a single non-clustered index. So yes, we do end up with lots of very similar looking indexes that have very similar sets of columns, but we build our non-clustered indexes for specific queries because we want to make sure that those queries are going to execute as fast as possible. Indexes are a simple cost-benefit analysis. How much storage is it going to cost me to create the index? How much time am I going to save? Storage is very cheap comparatively to time. Time is very expensive. If I shave half a second off every one of my queries by creating a couple of indexes that cost, say $1,000 to store on disk, that's probably going to be well worth it after the first few days of users running queries and waiting for those queries to execute. I read an article a few years ago that talked about how long it takes for somebody to lose their attention when they're waiting for something to pop up on the screen. So assuming standard customer service agent, sales rep, whatever. If it takes more than 2.5 seconds for whatever that employee is waiting for to pop up on the screen, they're now thinking about something else. And they need to then refocus their attention on what they're doing to get back to work. So if we can shave half a second or a second off our searches, bring them from 3 seconds down to 1 second to get them to execute, preferably even faster, then we're saving the company a lot of money because if it takes 3 seconds for the screen to pop up, because the index took so long, and they're focused on something else now, whatever they're talking about with their neighbor, whatever they're looking at on the web browser, and they then have to come back and focus on what they're doing. Maybe that's an extra 30 seconds that they're sitting around not doing anything that's work related. Suddenly this starts adding up to a lot of actual time over the course of the employee's day. The tables are sorted based on the order of the clustered index. So this is sort of true and sort of not. Logically, within the data pages, the data is laid out in however it needs to get into the data page. Data is simply inserted at the bottom of the page. Data is removed, rows are moved up. From a conceptual standpoint, SQL Server knows where all these pages are, or where all these rows are within the page. but the actual data is not sorted within the page because that would take a lot of time for SQL Server to deal with. Data is also not physically stored on disk in the physical order of the data, or in the logical order of the data. It used to be back in SQL Server 6.5. We were doing everything in the actual order of the data. Oracle does this, or at least they used to do it all the time. Now it's optional. So it's not, while you can assume that it's going to be sorted correctly, it's actually physically stored in a different order. Another one I see all the time is that clustered indexes are always required. This is definitely not the case, unless you're working in SQL Azure. Then they are required. So a buddy of mine, this was a couple of years ago now, was working in SQL Azure. He was using his girlfriend's account, who happened to be a Microsoft employee. He created a heap and went ahead and loaded some data in it, and then his connection got terminated for some reason. Turned out his girlfriend got a phone call about 5 minutes later from Microsoft Operations, wondering what the hell she had just done to blue screen the server in the Azure cloud. Turned out there was a bug in the original versions of Azure. If you created a heap and actually tried to load data into it, it would actually blue screen the entire box up on the data center, and the entire environment would come offline and have to be rebooted. Needless to say, he was not very popular that day with the Azure management team. They also found this bug and fixed it. He assumed it was simply a best practice to create clustered indexes on his table, and the 5 rows of data he was going to insert would not be that big a deal. Turned out it was. So indexes do have some downsides for sure. The biggest downside, obviously, is that indexes take up space. On large databases, it's fairly common for the indexes to take up more space than the actual data. If you ever look at the Stack Overflow series of websites, those websites are very well indexed, or rather the database underneath them is very well indexed, and takes up about 3 to 4 times as much space as the actual data tables that contain all the questions and answers for all the various websites. The reason for this is because of dynamic searching. The more dynamically searchable fields we have, the more indexes we need to get good performance out of the system. So this is a very big deal because a lot of applications today have the ability to search by a lot of fields. So we need to account for all the possible scenarios when searching through these fields, especially things like customer table. Customers may call in and ask to be looked up by their phone number, their tax ID number, their name, their email address, their customer ID, or some combination of all those things. So we have to have the indexes on the system to account for all these queries. Because of that, these indexes take up a ton of space. The indexes are all duplicates of the data based in the actual base table. So if we create 5 indexes on the first name table, or on the first name column rather, in the customer table, we're storing that information 6 times. The base table plus 5 additional non-clustered indexes. Adding indexes, or specifically non-clustered indexes, are going to slow down our insert, update, and delete statements. While they speed up select statements, they're going to slow everything else down. Full text indexes are even worse for this sort of thing, because the full text index does have to be maintained along with everything else. So I was working for a company a few years ago. We were running on SQL Server 2005 at the time, so we were using the old full text indexing engine. Now this company had an application that tracked what all of our customers were doing on their computers. So it's kind of like a big brother nanny cam sort of application, basically keeping track of what kids and spouses you were trying to divorce were doing online. So we tracked all your emails, all your instant messages, and most specifically, your web browsing history. And we tracked every single URL that you went to. One of the features of the application was that you had the ability to search through the URLs looking for specific words. So you could type in any word you wanted and search through the URL. So we tried doing this without full text index. Obviously that did not work very well because the URL was simply a nvarchar max data type. So searching through that with %sign at either end obviously scanned the entire table. When suddenly you've got 500, 600, 700 million records, that's just not going to work very well for a web-based application. So we threw full text indexing on this, changed the query to use the contains table predicate, and all of a sudden searches were going really, really fast. The only problem we ran into was deleting data now took a little bit longer than we were expecting. Without the full text index on there, we could delete 1 day's worth of data in about 2.5 hours. just deleting 1,000 rows at a time in a big loop. Once we added full text indexing, now suddenly it took 32 hours to delete 24 hours worth of data. This did not work very well at all. So we took the only solution that made any sort of sense. We removed the feature from the product. Made it so that users could not search through the URLs based on anything they wanted. They had to predefine the keywords they were looking for, and then we would tag those later. So this was one case where the business unit was willing to remove the feature because that was the only option that made sense. The only other option was going to involve throwing just tons and tons of money at this to try to find another full text style solution that would be managed outside of SQL Server and would give us the kind of performance that we needed. And frankly, we were a small company of 20 people. We didn't want to spend that kind of money. And we wanted to make sure that this system would continue to work as we continued to grow and add thousands and thousands of more customers. So be very aware of what the indexes you have are going to be doing and what impact having them is going to have on your system, especially things like XML indexes and full text indexes if you're moving a lot of data through this system. Using the wrong index can be slower than using no index or by just scanning the table. So you need to pay very close attention to those execution plans so you can see exactly what indexes you're actually using and see if you're scanning an index or seeking an index and if you're doing any other operations against that table. So the reason using the wrong index can be so much slower is because we scan through or even seek through the wrong index, get some huge number of rows. Well, we now need to refilter those rows again. So SQL Server is going to have to resort that data and then run a filter operation against it. It may need to actually get more columns than are available in the non-clustered index we just looked at. So it now may need to go do key lookups against the actual base table and go find all these other rows or all these other columns, join it all together in memory, do a merge join of some sort, or even a loop join. And if you've got a huge amount of data, that's going to be a performance killer. And then do a filter operation against that to return the rows back that you want. So we're now looking at potentially millions of I/O instead of just maybe a couple hundred I/O when it comes to actually finding all this data. With that much I/O being generated, you can almost be guaranteed you're going to be going down to the actual physical disk to get information. Whenever possible, we want to avoid the physical disk. Disk is slow. Even if it's a flash drive, don't tell this to the Fusion I/O guys out front, flash is still slow compared to memory. DRAM is always going to be the fastest thing we have, at least for the foreseeable future. So we want to make sure that we're always getting memory out of memory if ever possible, and almost never going back down to the actual disk to read data. That's why we need to throw more RAM in servers. So if we're going down to the disk to generate millions of I/O, now suddenly each one of these I/O, even though they only take a few milliseconds, are going to add up to a very long period of time that our users have to wait. A quick non-clustered index being added on all the necessary columns that includes all the columns we're looking for, and we'll be able to find all the data we need in memory once it's loaded into memory that first time, which usually happens fairly quickly on heavy load queries. If we're using data encryption, and by data encryption I mean we're actually storing encrypted strings in our database, indexing data and searching through data is almost never going to work correctly. The reason for that is because to properly encrypt your data, you have to salt the values that you're storing in the database. Once you've salted the values, they're effectively randomized. We no longer have any way of knowing how to do any sort of lookups against that information. The only way to search through properly encrypted data is to decrypt the entire column and search through it. So we need to come up with some other better way of storing these values to do lookups against it. Typically the solution is going to be decrypt the value, hash it with a static salt against the hash, and then store that hash in the database. Then when you need to do lookups, hash the value that you're looking up with the static salt in the same method you hash the data that you stored in the hash column, in your new hash column, and then do the lookup against the hash. That way we can at least index that data and the index will work correctly. And we're okay with storing salted hashes in the table because they're salted and there's realistically no way to get that initial value out of there. We don't want to store encrypted data without a salt because that's too easy to decrypt, and we don't want to put our users' data at risk. So there's some advanced index tuning techniques that are available within SQL Server when it comes to actually building your non-clustered indexes and your clustered indexes as well. So the first is fill factor. Fill factor is a fairly easy one. It simply tells the SQL Server how much white space to leave on the actual data pages within the non-clustered or the clustered index. So if we set this to a value of 80, it fills the pages to 80% whenever we do an index rebuild or an index reorg. When we're inserting, updating, and deleting data, SQL Server does not maintain the fill factor. That would just be way too expensive for SQL Server to do in real time. So that's where page splits come in, because they're less expensive than trying to maintain that fill factor. Padding is a very misunderstood setting. Not a whole lot of people actually know what the padding setting does when you're creating an index. What padding does is it tells the SQL Server to use the fill factor setting and apply it to the B tree. So if we've got a clustered index that's built on an identity column, we probably want fill factor set for 100, unless we're going to be putting data in the middle of that table somewhere. And we want padding set to off, because we don't need to maintain white space in our B tree whenever we do a rebuild, because all we're doing is sticking data at the bottom. Realistically, on most clustered indexes, we probably never actually need to do maintenance on those tables, because again, all we're doing is just putting data at the bottom of those tables. For our non-clustered indexes, if they're built on non-sequential values, in other words, anything other than an identity or a sequence, then we're going to want some sort of fill factor setting, probably 70–80%, depending on what data type you're using and how your data is laid out. And we're probably going to want the padding setting turned on. The reason we want padding turned on is because when page splits do happen at the bottom level of the index, we don't want to cause page splits to happen within the B tree as well. If padding is turned off, all the pages in the B tree are 100% full. As soon as we need to page split something at the bottom of the index, we now need to page split everything above that in the tree as well. So that could potentially cause 3, 4, 5, 6 logical and then physical writes to happen, just so we can insert one row into a table. So if we put the padding on, the B tree maintains all the white space, and we don't have all those page splits happening within the actual B tree itself. We have online index rebuilds if you're using the Enterprise Edition of SQL Server, starting with SQL Server 2005. Starting in SQL Server 2012, we have the ability to do online index rebuilds on tables that have blob data types. So text, n-text, image, varchar max, and varchar max, and var binary max. Keep in mind, if you are using text, n-text, or image, you're going to want to get rid of those data types as soon as you can. Eventually, those are going to leave the product. Data compression. This is a huge way to save space and burn a little CPU power. So again, we have a cost-benefit analysis that goes along with data compression. How much space do I have free in my database? How big is my database? And what does my CPU load look like on my server? If I've got a very large database that's got a lot of I/O performance problems, or that's generating a lot of I/O, and I've got a very low CPU workload on that machine, it might be worth turning on data compression on the actual index itself, or on the various indexes of the larger tables. This will make the databases a lot smaller, and will raise the CPU load on the server just a little bit to account for that. Typically, I see about a 2, 3, 4% CPU load increase for data compression when I turn it on very, very large tables. That 1.5, 1.6, 1.7 billion row table that my client has, that is completely compressed. And I think that server averages about 8 or 9% CPU. Granted, they have 64 cores, but it's still averaging a fairly low percentage. And keep in mind, there are two kinds of data compression available to you in SQL Server. There's page level compression and row level compression. Row level compression, one of the poorer named features in SQL Server, because it's not actually compression. What row level compression is doing is it's simply taking numbers that are stored in the database and storing them in the smallest number of bytes possible. So say we've got a data type numeric 18,12, and we store the number 3.5 in that field. We're still using 18 bytes to store that data, because that's how wide the data type is. If we turn on row level compression, we only store using the actual minimum number of bytes, which in this case would be about 4, to store the number 3.5. So it can have a dramatic amount of space saving on tables that have large amounts of numbers. Page level compression, on the other hand, is doing actual data compression like we would think of with WinZip or WinRAR or any of the standard compression applications. It's actually looking at all the data within the page, finding the duplicates and compressing it all down so we can store more rows within that same page. Page level compression also does row level compression as well. This also works if you have a big int data type and you're storing small numbers in it. Row level compression will help there as well because, again, you only need 2 bytes instead of the 8 bytes, but you're always using 8 bytes with a big int data type. New feature in SQL Server 2012 is the column store index. So this is a totally new and different approach to storing data. You've probably seen a half a dozen presentations on it since this feature was announced 2 years ago. The data is going to be stored via the columns, not the rows in the actual table. Once the data is stored into the pages on the disk, it's actually then compressed using a different data compression engine. In this case, using the Vertiprac or the X-Velocity data compression engine, depending on which marketing name you want to look at. This is a totally B-tree-less index stored in SQL Server. Whenever you are looking at column store queries, you will never see a column store index seek. You will always see column store index scans. This is very different from what we're used to looking for, so it takes a little bit of time to get used to seeing these sorts of things. You also need to look at the operating mode that the column store index is running in, because there's 2 different operating modes. There's row mode and there's batch mode. Row mode is going to perform very similar to the queries that we run today. So if you've got a billion row table, you run a normal query on it today without a column store index, and it takes 8 minutes to run, for example. We run it against the column store index, and it still takes 8 minutes to run. That means we're running in row mode. We need to figure out why we're running in row mode. That's typically going to take a little bit of looking at the query and comparing it against the best practices that Microsoft's documented in their column store white papers. Once we fix those problems, typically things like outer joins, filtering against string values, that sort of thing, and we fixed all these issues, then it's going to execute in batch mode. You can see this by looking at the properties of the column store operator in the execution plan. At the top of the operator, when you look at the properties pane, it's either going to say row or batch. It's going to be fairly straightforward as to which mode it's actually operating in. So there's a few use cases for the column store index. The first one being that we have a huge data set that's continuing to grow, and we have to keep performance the same. Maybe we've got a multi-billion row table that's being queried by a web-based application, and we need to be able to get the results back to the users very quickly on a timely basis within X number of seconds. Column store is going to be the great way to do that. Now, there is that whole issue of it's read-only. That's going to get fixed in the next version. Today, column store is basically being used for data warehouses. We don't want to look at using it for OLTP applications very often because of the fact that it is a read-only index. Once we create it on the table is basically read-only. When we are using it for data warehouses, we want to use it for huge data warehouses because it needs to be worth the time to create these indexes. Reports that take days, hours, weeks to run, these are the things we can solve with column store indexes. A friend of mine that works for a very large hosting provider whose name I'm not supposed to mention, but they have ads during the Super Bowl. If you watch the Super Bowl, you'll know exactly who I'm talking about. They were looking at the column store index to solve some reporting problems. They had reports that would take over a week to run a daily report. So this obviously was not going to scale. They were able to solve their problem by using column store indexes. That report went from taking a week to run to taking something like 7.5 minutes to run. Obviously, that was a very worthwhile investment. The only problem was it took like 4 days to build the column store index. So not the best solution under SQL Server 2012. SQL Server, or whatever the hell the next version is going to be called, that we'll find out at some point later this year, hopefully. That will be a solution that may actually work for them. Now, once we'll have the writable column store index in there. When we need to be filtering, aggregating, and grouping data despite the size of the data set. So we've got absolutely massive data sets that we need to work with, and we need to do fairly complex aggregations against them. This is where column store is going to come in very handy. So the limitations have been fairly well documented about column store and what it can and cannot do. So the biggest thing is there are some unsupported data types. I would not expect this to change in the next version of SQL Server. I would imagine adding this stuff in is a fairly low priority for the product team. So if you've got GUIDs, blobs, or numeric 19,2 or higher, while you can have those in the table, you cannot have those in the column store index. So when SQL Server 20, whatever the hell it's going to be called if the next version comes out, what are we going to do when we have writable clustered column store indexes, which were announced at the PASS Summit this last year? The answer to that is I have no idea. I'm guessing these data types are not going to be allowed to exist still. What you're going to want to do is change these out to some sort of other data type. For the unique identifier, convert that to an int, or a big int preferably, so that you've got some sort of number to work with there. How you do that, that's between you and your application development team. I would recommend a big stick. That'll help. Blobs, you're going to have to shrink those text strings down or in some way normalize that data to make it easier to work with. Numeric 19,2 or higher, yeah, I have no idea on that one. That's going to require some work with the development team to figure out why you're using that data type and how to shrink that down to something that's going to fit within the column store if you need to put that into a column store index table. We talked about the fact that it's read-only. Outer joins used in column store do not perform well today. This will probably be fixed at some point in the future, hopefully in the next major release of SQL Server. So if you're doing an outer join against the table with a column store index, do not expect good performance. I know this because the guy that wrote the column store indexing engine told me that this was the case. I trust him. He knows what he's talking about. Building indexes, fairly easy in SQL Server. Create index, whatever you want to call it, on some table, on whatever columns you want. Include whatever columns you want. Add a where clause if you so desire. With fill factor, pad index on or off, online on or off, data compression row or page. Fairly straightforward. The beauty of this syntax, if you want a clustered index, insert the word clustered in here. If you want a unique index, insert the word unique in here. Fairly straightforward language structure to work with within the actual database engine. SQL Server's data pages, or database indexes rather, are laid out in a series of data pages. I'm not going to dive into this too deeply. Feel free to download the deck, click on the links, those will take you to Books Online, and you can see exactly what's going on. Things to note, every index has a root page. The root page is the top level index or the top level page within the index. All navigation within an index is done from the top down. The number of intermediate level pages between the root page and the data pages, or the leaf nodes at the bottom, is going to be solely determined by the amount of data stored in your index. The more levels you have, the more work SQL Server has to do to navigate through that index. Every time you want to look for a row in a table, or in a clustered index, SQL Server does have to navigate this entire structure to find that row. So if we've got 1 billion rows, we may have 4 or 5 levels of intermediate pages, depending on how wide our clustering key is. So we have to navigate through that every single time. You can see how big your table or your B tree is fairly easily. There's a couple of different ways to do it. The first way, run dbccind and go searching through all the output, looking for the highest level number in the output. The other option's a little easier. Do select star from table where your primary key equals some specific value. When you do that, set statistics IO on. It's going to tell you a number of pages that were read. Subtract by 2, that's how many intermediate level pages you have. Remove 1 for the root, 1 for the data page, however many are left for the intermediate level pages. Question I get asked a lot, how big are the indexes I'm dealing with? sys.dm_db_index_physical_stats is going to tell you this information. It accepts 5 parameters: database ID, object ID, index ID, partition number, and the mode that we're working in. The default mode is limited. I would recommend using limited almost all the time. Limited simply looks at the root page and makes a lot of assumptions. Sampled reads the entire B tree, looking to see how much data is actually stored in the B tree, and again, making some assumptions. If you run detailed, it's going to look at every single page on the disk to see how much space is actually being used. If I ever caught a junior DBA running this with null values for the first 4 and detailed for this last one, that would be their last day of employment working for me, because that would mean they just ran a query that looked at every data page on the disk for the entire database, for the entire server. Needless to say, I would kick him out the door without much ceremony. If you want to know what indexes are being used and which ones aren't, feel free to download this code and take a look at it. I'm not going to make you copy it off the slide. You can either grab it from my blog or from SQLfool.com, because that is who I ungracefully stole this from, because I'm too lazy to write my own. All this is looking at is sys.dm_db_index_usage_stats. That is going to tell you how often indexes are touched, how often they are updated. This will tell you which indexes are being used, and most importantly, which ones aren't, that you can probably remove safely from your database engine or from your database. Don't reboot SQL Server and then remove the indexes based on this output. This output is reset every time you restart the database instance. So give it about 3 or 4 weeks, maybe a couple of months of uptime before you start really trusting the information out of here. Unless you have a client like mine that insists on rebooting their server once a week. I've got some additional reading on some of these topics that I've been talking about today available at that URL, dc.ac.co being my website, /res/table-indexing-net. I believe the slide decks will be posted up on the website as well, so you can grab it from there. Unfortunately, we have no time for Q&A. There's my contact info. I thank you all very much for coming. If you have questions, I'll be floating around. Feel free to come bug me about whatever comes to your mind, be it indexing or anything else SQL Server. Thank you very much for inviting me back to your lovely country. I had a great time last year, and I'm enjoying my trip again. I'll see you all around the conference.